And welcome everybody. In this video I'm going to talk about what you might expect on the first exam. So I'm going to go ahead and switch over to my camera here and talk about some things that we discussed very early on. We talked about the idea of conductors versus semiconductors versus insulators, and that conductors have between 1 to 3 electrons, lots of free space for free electrons to flow. Copper, silver, gold, all possible candidates for conductors. Okay, and in that space, I mean in the valence shell of the atom. Semiconductors like silicon, germanium, or gallium arsenic, 3 to 5 electrons, and they do have open spaces for those free electrons to pass. However, they require a voltage drop of typically, for a silicon diode, it's about 700 millivolts, and for a germanium diode, it's about 300 millivolts. So the insulators, 6 to 8, and all kinds of different insulators that we use: rubber, air, mica, bakelite, which is an official registered term, paper, especially paraffin-coated paper, glass, porcelain. So in these cases, the valence shell is full or almost full. Okay, so it's very hard to pass free electrons. Okay. So another thing we discussed was converting. So there's 1 coulomb for 6.25 times 10 to the 18th electrons. Okay. So the example I like to use here is if you had a piece of wire and you had your electrons flowing down and you were looking at one point right here, okay? And you said you had some super powerful electron microscope, which by the way doesn't exist, where you could count like this, because if you know anything about electrons, you can know their position, and you can know their was it the position or the speed, but you can't know both. So anyway, as they're passing down this certain point on a piece of wire, if you were able to count them, if you were to gather 6.25 times 10 to the 18th of them up at once, that's 1 coulomb. So if we were going to figure out how many electrons were flowing down at this one point to find the current, right, we defined current as Q over T. Right, that's charge per unit time. So if I said I have, I don't know, let's see here. Let's do 10.3 times 10 to the 23rd electrons past some point on a wire for, I don't know, 5 seconds. So that's what we saw. We counted that many going down this wire here, and we want to know how much current that is. Okay, what's the rate? So the first thing we need to do is not take this divided by 5 seconds, but we need to convert this into coulombs first, because this up here, the units are coulombs per second. So you have to convert this into coulombs first, so that's what we'll do. Need to get my calculator for this. So I'm taking, in my conversion here, I guess I'll show you what my conversion is. So to get coulombs, I take 1 coulomb over 6.25 times 10 to the 18th electrons times this number of 10.3 times 10 to the 23rd electrons, and that will give me charge. So 10.3 E23 divided by 6.25 E18. And I get 164.8 kilocoulombs. So I did a lot here. So we'll call this 165 and use 3 significant digits. 165 kilocoulombs. So that's a lot of coulombs. Okay, now I can take that number, remember it was for 5 seconds, now I can take current equals, the charge is 165 kilocoulombs over, it was 5 seconds. Okay, so I essentially take my number, divide it by 5, and I get, we'll call that 33.0 kiloamps. So that's not a very good example because we don't ever work with kiloamps, but that's the way the math pans out. Okay, so depending on what I give you, how many electrons we're counting past some point over some period of time, and you need to be able to figure the current out from that count. But you first have to collect all the electrons into coulombs, and then you can do your calculation. Okay. So the rest of what I'm going to do here is going to reference 3 resistors that I picked out of the parts kit, and they all come from the same bag just to make this example easy if you want to recreate this. So first thing I'm going to do, I'm going to end up building a circuit with these 3. But the first thing I'm going to do is I'm going to figure out if all of these are within tolerance or not to cover chapter 3. Okay? So the first one I have here, and I'll just lay these down and do them individually. So the first one I have is an orange, brown, gold. Okay? So we know that orange is 3, brown is times 10 to the brown is 1, and then plus or minus 5%. So this is a 330 ohm plus or minus 5% tolerance resistor. Okay? Now I'm doing this off camera, but if you want to know how to do a resistance measurement, watch the resistance measurement video. As I, at least in this part right here, I'm just going to measure it. And for this measurement, because it's above 200 ohms on my meter, I'm going to use the 2K ohm range to get the best resolution. So I'm only going to get 3 digits here, but that's okay. Okay, so this is my orange, brown. This is it. So again, I take the body of the resistor, my thumb and forefinger. I know this isn't showing up on video right now, but I'm getting 325 ohms. So I actually measured 325 ohms. That's pretty close, but let's see how close it is. Okay, now if you want to do the maximum and minimum calculations, all right, essentially you're taking plus 5% and minus 5%. So I showed you in the resistance video the way that I calculate this is essentially I take 330 times 1.05 because that's 105%, right? If no tolerance is here, then it's exactly on. But if you're giving it a range, then it's 5% above 1 and it's 5% below 1. So 330 times 0.95. Okay? So that's 95% of this, and this is 105%. That's all this means, this plus or minus 5%. It's within that tolerance. 100% is always whatever the nominal value is. So let me do both of these calculations since I got it up here. Times 1.05, that's 347. 347 ohms. So I can already tell that it's within, well, that's the top range. Let's see what the bottom range is. So now times 0.95, and we get 314 if we round up. So, does this fall within this range? Yes, it does. Okay, so that's one of my resistors that I'm going to use over here. So 325 ohms. I have that one available. Okay, let's go ahead and do the next one. And this is for a 330 ohm. Okay. Now, where's my next one? So that's my 330. This is Red, red, brown, gold. Red, red, brown, gold. Okay, and I believe all of the resistors in your kit are gold, so they're all plus or minus 5%. So at least for your lab calculations, it makes this pretty easy, right? So red is 2, brown times 10 to the, brown is 1, plus or minus gold in the tolerance band is 5%. So this is 220 ohms plus or minus 5%. So now if I want to find the maximum and minimum of this resistor, I take 220 times 105%, or 1.05, and 220 times 95%, or 0.95. Okay, and I put the percent on here. I shouldn't have it. Just 1.05 and 0.95. If I did that in the previous example, that's a mistake. It should just be 1.05 and 0.95. Okay, so the maximum top end I would expect is 231 ohms. And the minimum, 209. So let's see if my particular resistor falls within that tolerance band. Or did I get one that's out of tolerance? Okay, again, I'm going to be just outside of the 200 ohm range, so I'm going to stay in the 2K ohm range on my meter. And it measures 216 ohms. So that one is also within tolerance. So I have another one up here I can use. So let's make this over here. This is 216. And that is for a 220 ohm resistor. Okay. Now let's go ahead and do the very last one. So again, I'm just using the ones that are out of your kit. If you just want more practice, you certainly can just come up with whatever colors that you want. This final one that I have is an orange, white, brown. Orange, white, brown, gold. Okay, so orange is 3, white is 7, brown is times 10 to the brown is 1, plus or minus 5%. Whoa, that's 5%. So this is a 370 ohms. So they're all very similar because they all came from that same bag in the kit. So 370 ohms plus or minus 5%. So to find the maximum value here, 370 times 1.05, 370 times 0.95. So let's see what the max and min are here, and then we'll measure it. So 389 ohms, and the floor of that, or the bottom, 352 ohms. So there's my range that the manufacturer is telling me this particular resistor is in. But I'm going to verify it because sometimes they are wrong. Sometimes there's a couple of bad ones in the batch. And I measure 386. Woo, just inside, huh? All right, so now we've got a 386 ohm. That was our 370. So this one measured really high. So if we were talking in terms of percent error, I'm not going to do those calculations here, but for the percent error, you know, it's always measured minus expected over expected. So measured value minus expected value over expected value, whole thing times 100%. Okay? So you can look and see in each of these cases, this one, because it measured lower, that's going to give me a negative because the measured value was lower than the actual. So it's going to give you a negative. So you're going to get a negative percent error for that one. This one also measured lower than 220, so you would get a negative percent error. This one, however, because it's greater than the expected value, the nominal value or whatever, so that's, it looks like 390, but that's 370 because of how I write my sevens. So that's 370. So the measured value was more, and so I would expect a positive percent error in that case. Okay. All right, so there's my three values. So that takes care of chapter 3, and also talking about the the potentiometers and measuring those. Okay. Let's go ahead and create the circuit here. And so what I'm going to do over here on this part of the board is I'm going to show you how I would make the connection on the breadboard. Okay, so I'm going to sort of wire it up, so to speak, like you would see on the breadboard, and then I'm going to recreate it on the breadboard and then measure the components. Okay, so my circuit here, I've got my, I'm going to call it my 9.4 volt battery because that's the last time I measured it under load, that's what it was producing. So 9.4 volts, and I'm going to use the nominal values, 330 ohms. So just a 3 resistor series circuit. So 330, 220 ohms, and 370 ohms. Okay. So the normal circuit analysis on this would be for me to, step 1, find the total resistance. And so that's going to be 330 ohms plus 220 ohms plus 370 ohms, which gives us what? I don't want to do this in my head. I'm too tired. 550 plus 370, 920. 920 ohms. Okay, so that means that the current, the one and only current, because this is a series circuit, so the current is 9.4 volts divided by 920 ohms. And I get 10.2 milliamps. So, for my circuit, I expect to measure 10.2 milliamps. Okay, as far as the individual voltage drops, I'm going to show you how to do voltage division again, because you need to get that skill down for what we do in the second half of the class here. Okay, so voltage division. So I want to know the voltage drop of each one of these, and I'm not going to use the current to do it. I could use Ohm's law, right? I could just say, well, I know what the current is now, and so the current times this resistance is the voltage drop. The current times this resistance is a voltage drop, and the current times this resistance is a voltage drop. Those will all add up to 9.4 volts, okay? However, I don't want to use this right now. I want to work on my voltage division skills. So I say the voltage of the, and what was the, I erased it, it was 920 ohms. So we need that information if we're going to do voltage division. So the voltage of the 330 is going to be, remember, it's the total voltage available times the ratio of the individual to the total resistance. So 330 ohms over 920. The second one, for the 220 ohm, 9.4 volts times, in this case, 220 over 920. And then the voltage of the 370, 9.4 volts times 370 over 920. Okay, so let's find out what voltage drops we're going to expect here, and then we will double check and see if these all add up to 9.4 volts. So 9.4 times 330 divided by 920 equals 3.37 volts. The 220, okay, all I have to do is come in here and edit mine to say 220 and 2.25. So what is that, like 5.5? So this one should be like roughly 4. So this is going to be 370 over 920 this time. 3.78, very close. Okay, so now I take 3.337, whoops, not 337, 3.37 plus 2.25 plus 3.78, and I get 9.4 on the dot. Okay, so I think that those are good. All right. Now, in terms of how I would wire this up, okay, I'm going to draw. Okay, this is going to be my bridge that goes through the middle of the breadboard, okay, which means that, you know, I'm counting up here. 1, 2, 3, 4, 5. Each one of these 5 are connected underneath. This is what I explained in the breadboard video. Okay, I'm not going to go all the way across here, but I'm going to do enough of them just so you get the picture. And I guess it's unfortunate I'm using red because you do have red and blue on your breadboard, but that has no, remember, that's just coloring. They could have made it purple and whatever, okay? And then remember, across the top you've got, right? And then if I use, I thought I had another color. I don't know how well the orange is going to show up here. We'll see. Yeah, it's coming up. Okay. So that's the general format of your breadboard. Okay. So I'm probably going to connect in, I guess I can put these underneath too, where we have the, so obviously you have the other side, but I'm talking about down here. All those. And all these. Okay. So I'm probably going to come in with my 2 leads for my power supply. Let's say that I put the positive lead in here. So this is 9 volts positive. And then right here on this line, I put the negative side of the battery. Okay? So there's my 9 volts and there's my 9 volts. And so those go off the page here. Okay? So now I have 9 volts available on this entire line here. So the first one I put in is probably the 330. And let's go ahead and put it, I'm going to attach it right there and right there. So that's my 330 ohm. Okay? Now I need to connect the 220 somewhere on this leg here because I'm going to make this connection up here. Okay? So on this group of 5 here, I've got this connected to that rail. Okay? So now I'm going to connect underneath here. And now this is my, what is next? The 220. So this is 220 right here. Okay, so you can see I've got them connected with this one leg here on that group of 5. All right, and then the next one, maybe I bridge the gap. Or I guess I could just keep going out this way. It doesn't really matter. Let's go out this way. So on this group of 5, I could put it up here. I could put it down here. Let's put it down here. Why not? And put the other leg in here. So now this is the 370 ohm. Okay? Then I have to take this leg somewhere on here. I'll just take it from here. This has to come down here to the positive. Okay? Now remember, this is the negative up here. This is the positive. So I actually have this drawn backwards. So I can actually do 370 here, 330 here. And now it matches this. So we come out of the positive terminal of the battery, go into one leg of the 330 ohm, and then the other side of the 330 gets connected to a leg of the 220, and then this other side of the 220 gets connected to the 370, and then the 370 leg gets connected to the negative 9 volts. Okay? So that's an example way that you could wire this up. Okay? I'm going to go ahead and pause now and set up for the actual measurement and construction of this on a breadboard. So now we're going to go ahead and build that circuit and see if what we did is correct. I think it is, but let's go ahead and build this. Okay, so the first thing I had was the 370. Notice how I have my power. I'm not showing the battery here, but it is connected to my 9-volt battery, and I've got my my negative at the top like I had in the example, and I also have the positive at the bottom like I had in my example. Okay, so at the very, very top I had my 370 ohm, and that's this one. So I'm going to plug in here and a few places down here. It doesn't really matter, just some place to stick it. I'm going to have a piece of wire that comes back to here, okay, so that I make that connection. And then anywhere, so then the next one is the 220 ohm, and just anywhere on this group of 5, make a connection, and then place it over here somewhere, like maybe right there. Okay, so there's my 220, and I don't know if I can show that any more clear or not. Looks like it. You can see that those two are on the same group of 5, and that these two are on the same group of 5. And so finally, I need my 330 ohm to start off with here. And pull it right there. Okay. So now I need a wire going from that one over to, let me make a big arc here with my wire so that it fits a little bit easier. From here, and remember, I have access to that positive 9 volts the full way down here. So I'm going to go ahead and pop that in right here. Okay, now right now the circuit is live and running because I didn't put a switch on it and I didn't leave anything unconnected. So right now it should be working. So let's find out. All of my voltages are above 2 volts, so I'm going to stay in the 20 volt range on DC volt range on my DMM. So what I'm going to do now is I'm going to pull back just a bit. I'm going to put my DMM in frame, make sure there's no glare, and I'm just going to start measuring these. So my first one, 2.9 volts. And let's see here. What am I doing under, how about on the outside here? What am I doing? It's saying only 8.28. So my battery must have been left on because it is a much, much lower voltage right now than what I had. So that the 9.4 volts that I was using before, that's incorrect. So what I should have done is I should have measured it right now while it's sort of under load to see how it would be performing, because it is no longer 9.4. So as I said, I must have left it connected or something, because it drained 1.2 volts out of it. So so now my calculations are going to be a little bit off. That's no big deal though. I'm still looking for the same ratios. Okay, so here we've got, if we measure this again, 2.9 volts, 1.92, and 3.44. Okay, so those are roughly the same ratio, even though they're not the same actual voltage. If I did the calculations with my, again, the way I'm getting the total voltage here is I'm just measuring all the voltage drops across the resistor. I'm not even measuring the actual volt, the battery itself. So there you go. So outside, you know, now my probes are essentially connected directly to the terminals of the battery, and I'm only getting 8.25 volts out of it. Okay. So that's the thing with using these 9-volt batteries, is you got to remember to unplug them, you know, and you can't just leave the circuit sit like this when you're done. You need to at least pull one of them out, and so now you can see that there's no voltage across anything. So now I've turned the circuit off. So if you want to wire one of your switches in, you could do that as well. And then you could have like a little toggle switch where you turn it on and off. Okay. So what I'm going to do is find my paper here, and I'm going to write down these, and I'm going to redo all the calculations with an 8.25 volt. So that's what I measured. And then the first one was 2.9 volts. The second one was, what, 1.92 volts. And I've already forgotten the third. I think it was like 3.4 or 2.42, 3.42. Let's measure it again and see. Just to be sure here. So I've got the circuit live again. 2.9, 1.92, 3.44. Works for me. 3.44. Okay. Okay, so I have reworked the problems using 8.25 as my source voltage this time, and now I get 2.96 for the 330, 1.97 for the 220, and 3.32 for the 370. So they're still not exactly the same, and here's why. So nominally, this should be 370. What we actually measured was like 382. So that's why this one is getting more with 3.44 volts, okay? The 220 measured less. That's why it's not measuring as much here, and also because this one was bigger. But same thing here, right? We measured 325 ohms, and so this should be 2.96, but it measured lower than 330, so that's why we're only getting 2.9. Okay, so it looks like everything worked. Everything matches up. Very good. On to parallel. Now we're going to look at using those same value resistors and now putting them in a parallel orientation, and I've now changed the battery to what we just measured, which was 8.2 volts as opposed to the 9.4 that I thought it was. And boy, I just said that and I didn't even disconnect it again. So make sure you disconnect your circuit, otherwise you're going to drain your battery unnecessarily. Okay, so I probably had that running overnight. So anyway, you know from our parallel discussion that if we want to find the total resistance in our circuit here, all of these are wired in parallel, and so if I want the, whether I had 2 of these in parallel or whether I had 15 of them in parallel, I use the same equation every time, and that's just to take each one 1 over the value, so 1 over 220 plus 1 over 330, take the whole quantity to the -1, and I explain where that comes from in the parallel video. So this is going to give me the total resistance for my parallel circuit. So let's go ahead and calculate that. 1 divided by 220 plus 1 divided by 330 to the -1, and we get 132. So as you know, the very first check you should say is this value less than the smallest thing I have in parallel? And it is, right? 220 is the smallest. This is smaller. It always has to be smaller. That's the very first check that you should look for, okay? Now I can go ahead and find the total current here. So the total current, I have 8.2 volts divided by 132 ohms. And what do we have here? Divided by 132. So my total circuit current is 62.1 milliamps. Okay. So in the series circuit, we had what? 920 ohms. That's a lot more resistance against that battery versus just 132 ohms total. Okay. It's like roughly 1/9 or something like that, 1/8. So anyway, I expect a total current of 62.1 milliamps coming into that first node out of the source. Okay, so that means now I have to find each of these currents. All right, one way I could do that is to just use, again, I could just use Ohm's law. Since I know that these are wired in parallel, I know that they're going to drop the same voltage with whatever they're in parallel with, which is this 8.2 volt battery. Okay, so I can take 8.2 volts divided by 220, find that branch current. 8.2 volts divided by the 330 and find that branch current, or I could use current division, which is what I'm going to use. So we get some more work with that. And the reason why I want you to learn the voltage division and the current division is because of, again, the second third of the class, Chapter 7, Chapter 8, Chapter 9. It's going to become an invaluable tool. Okay? So, to find the current through the 220, okay, I know what the, I just erased it. It was 132. You got to know what the total is. Double check, make sure that's what I got. Yeah, 132. Okay. All right. So in this case, we do the total current this time. So 62.1 milliamps times, now this time the ratio is flipped. It's the total over the individual resistance. So this time we have 132 ohms over 220. Okay. Now you'll know if you got your ratio wrong in either case when you come out with an answer that's higher than your total. You can't have a total current, you can't have a branch current that's higher than your total. So if you had these flipped, that ratio is going to give you more than 1. Right now it gives you less than 1. There goes my camera. Off, on. Should reinstate it. Goes. Okay, now it's working. Okay, so 132 ohms total. So now I can do the math on this to find the branch current. So 62.1 times 132 divided by 220. And I get 37.3 milliamps. 37.3. Okay. All right, so now let me find the current of the 330. So 62.1 milliamps. Now this time times the total over the individual, 132 over 330. So I just have to change the last three numbers here. 28.4 milliamps. So now you say, does that make sense? Does it add up to the total? You take 37.3 milliamps plus 28.4 milliamps. And I get 60, let's see, 37.3, 28.4. Is that what I got up here? 37.3, 24.8. This is wrong. See, this is why you check. 24.8, not 28.4. 4.8. Now, when I put in the right numbers, 62.1. Okay, there we go. So those are my two branch currents that I'm expecting. So the smaller one should get the bigger current. That's another check, 37.3 milliamps, because there's less resistance here and more resistance here. And then this one is the 24.8. Okay. Now, the trick question here is, well, what do we do about the voltage drops? Well, the trick question is that there is no calculation for this because they're all in parallel with the battery. So the voltage of this is 8.2. The voltage of this is 8.2. Okay. Now, in terms of how I would wire this up on the board, I do a little bit more wiring with my parallel circuits because of, with a series circuit, and I didn't do this in the last example, but a series circuit is very easy to just insert your ammeter anywhere in the circuit. With parallel circuits, you have to be more careful because you have three potential current measurements that you could make. You can make the total current measurement, you can also make this branch current measurement or this branch current measurement. So you have to leave room for three possible current measurements. So I'm going to bridge the gap here with my resistor. And yeah, I don't have any other colors. So I'm just going to connect from here over to here. Okay, and this is my 220. Okay, so just a spot over here and a spot over here. And then I'm just going to put somewhere over here in parallel just so I give myself enough room. This is the other resistor, and this is the 330. Okay, this time I have this oriented to where this is the positive 9 volts coming into this top red rail. And then on the bottom blue rail here, I've got the negative 9 volts from the battery, or in this case, it's the 8.2. But you know what I mean when I say 9 volt. I'm talking about our 9 volt battery, okay? All right, so what I'm actually going to do is I'm going to have a wire from here to here, and I'm going to have a wire from here to here. That way I can insert my ammeter here or here. I'm also going to do another wire from, let's say, here to up here. and from here to up here. All right, so you can see I've got it spanned across the whole breadboard. I could connect this to any one of these group of 5 here, but I've just got it on this one. So from here to the rail, from here to the rail, the positive 9-volt rail, and then from here to the negative 9-volt in both cases. So I'm going to be inserting my ammeter. If I want the total circuit current, I would have to do it before the 9-volt lead and this rail. Okay, and I'm going to do that. I'm going to measure it up there. Then I'm going to do the individual branch currents, and so to do that, I can pull from right here and undo that, and then have it from, kind of place it in between. I can pull this here, and then have it in between that wire and this terminal here. So what I'm doing is I'm setting this up so it's easy to make a good ammeter measurement. Okay, I'm going to keep these measurements up here, and I'm going to go ahead and construct this circuit. So here we go. I have got the circuit created, and I don't have it on yet because I don't want to waste my battery. But anyway, you can see here that I've got the 220 and I've got the 330, and I've got them each attached as I said I would in the drawing. Here's my positive terminal here, and if I were to connect this, I would have a live circuit. Okay. Now what I've done for my current measurements here, I have to be very careful not to touch my camera because it doesn't like to stay connected for whatever reason. So here we go. All right. So what I've done is I've taken the ends of my probes just to make these easier since I don't have a lab partner to work with. And there we go. See, I bumped the camera and it goes to a still shot. Just great. This is what happens when you buy cheap cables, by the way. Don't do it. Okay. Whoop. All right. So there I've got it in, I'm measuring in milliamps, DC amps. And so I'm going to go ahead and connect the actual circuit. And so now it is live. Okay. It is running right now. So I have attached some alligator clips to my probes, and then on the end of my alligator clips I have a little piece of wire, and so that's where I'm going to put my current meter leads in. Okay, and so this red one is my red lead, and this black one is my black lead. So I'm going to measure the total circuit current first, and I'm actually going to do that. Let's see, up here at the very top, I'm going to take this out. Okay. Actually, I'm going to leave that in because I need to draw that current too. Put that back in place. And so what I'm going to do now is I'm actually going to take the positive terminal and put it over here. And so now I can connect the red terminal of my meter to the positive terminal of the battery, and then take the other side of my ammeter and now go into that top rail, and it should give me my total current. And I should mention I'm in the 200 milliamp range because I'm expecting this to be 60 milliamps, so it's too much for the 20. So here we go. Okay, so there we go. So I'm getting 52 milliamps, which is well below the 61. So my guess is that my battery has already drained some more. Would be my guess. But anyway, I'm getting a total circuit current of 51.6 milliamps. Okay. Now, if I wanted to do the individual branches, I'm going to go ahead and unplug this, put my power back where it came from, and now I want to measure an individual branch. Okay. And so probably the easiest way to do that is to just remove, like, the bottom wire there, put your positive lead in where it touches the lead of the resistor, and then put your negative lead into the bottom terminal. So there we go. There's 32.6. Okay, so that's the 220 that we're measuring right now, and we expected 37.3. So that's what's going on, is the battery is still draining as we speak, and so it must be lower than the 8.2 volts that I assumed that it was. Okay. So if I want to measure the other branch, I can take my meter out. So if you ever get this, like on the exam, or if you get it on your labs or whatever, make sure you measure what your voltage is every time out of your battery. Okay, so I'm going to do the same thing with this other branch. I'm just going to take that bottom wire out, and I'm going to put the positive lead of my DMM into the leg that touches the resistor, and I'm going to put my negative lead of my DMM into the bottom here. So there we go, 21.6 milliamps, and we expected 24.8. So we're about 3 or 4 milliamps off in each case. And so that's, if you did the ratio of the two, they would still have the same ratio as 37.3 and 24.8. Okay? But anyway, I think that's the easiest. If you don't have a lab partner to help you, then, you know, putting these alligator clips on your leads out of your DMM, and then having a little wire that you can put in the board just makes it a little bit easier, because right now I'm not touching anything and it's making the measurement. Okay, so what I am going to do here is I'm going to go ahead and put this back under load and connect this from here to here. So I'm drawing the same total current. And I'm actually going to go into, I'm going to have to pull this off screen here. I'm going to go into DC volts. So I got to switch my leads around. Okay. And so I'm going to measure that outer voltage. So now that I've got these connections on here, I can just plug right into where my 9-volt positive lead is and where my negative lead is. Oh, there we go. So you can see that's all the way down to 7.03 volts. So again, I must have left it on earlier. So as you're making these measurements, you may want to, you know, just kind of watch what's happening. It could be performing differently because these are being drawn in parallel and it's drawing a higher current. That could be affecting the operation as well, because we have to take into account that internal series resistance of the battery. Okay, so I'm only working with a 7-volt total here. So if I had my sheet here, let me write this down. So I really had a 7-volt battery, and my measurements were, gosh, what were they? I guess we can make them again real quick, and then I can write them down. Okay, so I'm going to go back to my current measurement just so you can see this again. To the 200 ohm range, 200 amp range, I should say. And instead of doing that nonsense on the outside, which essentially shorts it, I want to be from here to here. So again, there's my negative lead. I'm just going to touch my, okay, so 52.2 total. Let me get that written down. 52.2 milliamps total. All right, so let me go ahead and put this back in. And this is my actual power to the circuit, and these two are my leads. Okay, so again, I'm going to pull this bottom one out, and I'm going to put my positive lead right next to the terminal there, and then also for, and we got 32 milliamps there. Okay, fair enough. Now I take my leads out, I plug this back in, take this one out. Now again, my positive lead touches the same 5 as the resistor, and I put my black lead in the hole in the ground, 21.3 milliamps. Okay, so that adds up actually to like 53.3, so we're within a milliamp here. All right, so I'm going to go ahead and then turn this off, and I'm going to go ahead and write this all out on paper, and then we can show if we still made good calculations here. Okay, and as you can see, I went ahead and redid the calculations here. So now I had a total circuit current of around 52 or 53 milliamps. That's what I actually measured. I think it's closer to like 53. But anyway, So I should expect from the 220, 31.3 milliamps, and from the 330, 21 milliamps. And here's what we actually got. So that matches up pretty well if you take into account the actual voltage of the battery during this simulation here. Okay? So everything that you've seen here is part of the written portion of the exam, and as far as the lab portion of the exam, it will be on the construction that I did. You'll have to do series circuits, you'll have to do parallel circuits, and you also have to do them in multisim. Okay, so make sure you review all the videos and go back through all of your notes. And remember, because this is virtual, you have the opportunity to go back and watch all of these videos, whereas normally in a face-to-face you wouldn't. So take advantage of that, okay? And good luck.